Hi, everyone. My name is Yan Li, and I'm excited to have an opportunity to take you on an interesting journey. Before we discuss the specific story together, I want you to imagine something with me. So we have a population C, and we want to know the ancestor of C, and we labeled ancestor of as A and B, and we really want to know how long ago A and B met relative to today. To achieve this goal, we should know two time periods. The first one is how long ago population C lived, and the second one is the time period between the time that population A and B met and the time of population C. And then we combine these two time periods together to get how long ago A and B met relative to today. Next, I want to explain what kind of mathematics I will use in the research. They included collaborating, say, carbon 14 days, negative binomial distribution, convolution of two distributions, and simulation. The first one is collaborating carbon 14 days. Imagine you find an old wooden object and you want to know how old it is. Scientists use a method called radiocarbon dating for this. It works because we know living things absorb a radioactive version of carbon from the atmosphere, and after they die, the carbon-14 start to disappear at a known rate. However, the amount of carbon-14 in the atmosphere has changed over the century. It's not consistent because of some natural factors. So if we want to know how much carbon-14 is left in something without considering these changes, so we need collaborating the carbon-14. Scientists have started trees and other materials that we know the age to see how much carbon-14 they had at different times in the past by comparing these with the amount of carbon-14 in our old object. We can collaborate or adjust the age calculation to be more accurate. So we can use R to sorting data and calculations. And there is a specific toolkit in R called R carbon. So we can use R carbon to handle our a collaboration. So as scientists take all these ranges of days and put them together into one picture. The picture shows which time periods have the most votes from all the dated pieces. The highest peaks on the picture are the time periods where they think the most activity happened. This picture is called summed probability distribution. In the right graph, we can see the time range is from 4,000 to 5,000 years, called BP. The summed probability is from 0 to 0.05. We can see from 4,400 to 4,600. The population C has the highest peaks. Then we will explain what is the negative binomial distribution. The negative binomial distribution is like playing a game where you keep trying until you win a number of times. So it's a way to guess how many tries you will need. So it's a type of mathematical rule that predicts how many attempts might be necessary to achieve a specific number of successes. In the graph, we can see x-axis is from 0 to 138 and represents number of trials needed to achieve our successes. The y-axis is from 0 to 0.06 and represents the probability to achieve the specific number of successes. From 41 to 59 trials needed to achieve around 9 successes has the highest peaks. So next we will discuss the convolution of two distributions. In the research, we will multiply each probability from the sum of probability distribution and the corresponding probability from negative binomial distribution. And then we add all elements together to get the results of convolution of two distributions. In the graph, we can see the final result of convolution, and we can also see the probability of how long ago population A and B met in the time period. Finally, I will introduce the simulation research method to you. In this case, I use Monte Carlo simulation research method. The Monte Carlo simulation is a algorithm that relies on repeated random sampling to obtain numerical results. Random sampling is the most crucial step of this simulation method. A set of random values is generated through random sampling and its probability distribution. Then we put these random values into the model that we created. Next, we will get the output from the model and random values. By repeating the simulation method, we can get different outputs. We analyze this output by distribution that explain the standard deviation. In this case, I set 1,000 number of simulations, which means that my simulation will be done 1,000 times by computer. I add noises in my data, adjust the standard deviation of inputs, and also add noise in R and P, making values uncertainty. Then I put uncertain values into models, so I could get different outputs compared with the outputs that I finished before. In the graph, you can see the standard deviation of the convolution. This is a very narrow range, indicated that the convolution results are consistent across your across the 1,000 simulations. Each convolution process involves combining two sets of data, the SPD and the negative binomial distribution in the case, and the standard deviation is the measure of the spread of these combined results. A low standard deviation suggests despite a randomness and any noise in the data, the outcomes from the model are stable and not vary widely from one simulation to the next. In the future, I will continue to implement the research and verify the results, try and implement other methods, report the benchmarking for code run times, and submit the final report. Thanks for your listening.